All right, good morning. My name is Cyrus. I'm presenting to you on Conduit, which is a new library we're developing. I'm presenting on behalf of myself, Brian Regine, and Adam Coonan at Lawrence Livermore National Laboratory. And we're all computer scientists at Lawrence Livermore. For those of you who don't know where, can we close the back doors? Sorry. All right. Is that better? Okay, thank you. So again, I'm Cyrus. I'm presenting on behalf of Brian, Adam, and myself. We're all computer scientists at Lawrence Livermore National Laboratory. For those of you who don't know where that is, we're in Northern California, about 45 minutes east of San Francisco, and we're a national laboratory, part of the Department of Energy. First things first, I guess I should say if you Google Conduit, you might find something about a virus. That's not us. Or something about virus is a bad word, maybe adware is a better word, but that's still not us. So we're not focused on that. We're focused on providing a library to help with in-core, meaning in-memory data exchange for HPC simulations. So it sounds like, that hopefully will be better. I'll hold it. I'll hold it. There we go. Okay. So this is a library that is focused on C++, Python, Fortran, and C, and those are the things that are important in our ecosystem. I'm going to kind of motivate that a little bit in this talk. I think it's quite important, and it's Python 2 and 3 before you try to burn me at the stake. Even though some of us HPC folks are still stuck on Python 2, quite honestly. It's an open source project. It's a couple years old. And we are now starting to use it in our applications at Livermore. So that's one of the reasons why I'm here to talk to you about it. So it's a simple library, and it's a collaborative development effort. There is no Conduit project. There is no Conduit project leader. It's developed by myself and a couple other people. So I work on Visit, which is a large open source scientific visualization analysis application. Brian works on a multi-physics simulation application, so a big monolithic production code at Livermore, and Adam works on a deterministic transport package. So each of us come from different teams, different backgrounds, but we're all computer scientists supporting physics simulations. And many other people have contributed as well. So it's not just us. The ideas in this case are kind of more important than the code. So there's been many other people at Livermore who have helped us out with this. And one of the things I really want to mention, because I think it was a fantastic process, is we had a clinic project with Harvey Mudd College, which is sort of one of their senior capstone projects, to help us really get our act together on Conduit and build it into a better tool for our HPC applications. And when I say, in this case, we focus this project on proxy applications. When I say proxy, that's a very overloaded term in computer science. What I mean is we have big physics codes at Livermore, and they're hard to wield, they're hard to change. So we created these bite-sized things called HPC proxies, or mini apps, that are 3 to 10,000 lines of code, not 800,000 lines of code, to experiment with new programming models and things. And these students used Conduit in that aspect. So that was really good, and it helped us get our act together and helped us solidify a lot of our important use cases. So, still haven't told you what Conduit is. That's still on purpose. Hang in there. I want to talk to you a little bit about what has got us thinking about this. So we live in the Weapons Simulation and Computing program at Livermore, and we're part of the computational physics element. So what we do is we develop big multi-physics simulation codes that run at the largest scales on supercomputers that you see on the top 500 list. And I want to give you a little bit of an idea of what the program entails. So we have about 120 different developers. These aren't computer scientists. These are a mix of computer scientists, physicists, engineers, software quality people. So a very multidisciplinary set of team. These are the people who write these codes. There's about 15 of these project teams, and they have a very long life, so 15 to 30 years production life. And it's about 2 million lines, or 12 million lines of code, not 2 million. 12 million lines of code, and that's counted in some sane way. And there's over 100 third-party dependencies. So our life's kind of complicated. There's a diversity of programming language used throughout, C, C++, Fortran, Python, Lua is a new entrant in there, and there's a lot of different types of data. So I feel that computational physics efforts are a microcosm for the broader HPC simulation community. Of course, we don't capture everything, but we have enough complexity to be able to claim that. And I want to give you an idea of what we mean by a multi-physics simulation application and what we mean by, what are the pieces of the puzzle in the ecosystem. Now, this isn't the people who write the operating systems or the file systems. This is just the application section of our program. So multi-physics applications have lots of pieces. The details aren't important other than it's complicated. There's a lot of computer science. There's a lot of domain physics. And those are either physics packages which deal with time stepping, basically integrated time steps, or they could be libraries that help you get material properties, things like that. In addition to that, a user doesn't just go and sit and run a code. They have to do a lot of things. We all know the workflow of a human is important, so there's workflow applications as well. And those include things for setting up your problem, getting your CAD geometry in, for example, visualization analysis, so making movies, doing integrals, things like that, and also a big effort at Livermore is on uncertainty quantification. So that you can think of this as sensitivity studies that are run. So as a developer in computational physics, what do you see? So this is our reality. So when I say Python here, I include things that do use C and C++ and Python, like NumPy and things like that. But our life is predominantly C++. Then there's Python, Fortran, and Lua. So this is how we deal with things. But Python plays a prominent role throughout the whole workflow. And if you're a user of one of these codes, what do you see? So for the physics simulation applications themselves, most of them have a custom input language. So we have about 5 of these big multi-physics simulation applications. Most of them have a custom input language. There's some that use Python to drive everything, and there's a new one that uses Lua to drive everything. And from a workflow perspective, there's Python and GUIs. And of course, we love Python more than GUIs, but we won't go into that more. So throughout all this, all this code, all these developers, data coupling is a kind of challenging thing to do. And it's an important part of the workflow. It's an important part of the development aspect of things. So one thing I will say is that in-core data exchange has received less focus than file-based. So file-based has become the predominant way of doing business. You want to get from one part of a code to another part, you write a file. There's some cases where we do transfer meshes and memory and things like that, but that's not the predominant way that we do work. And one of the reasons why it isn't the predominant way we do work is in-core data exchange across a diverse set of codes is hard. It's a hard problem. So that said, if you look at the HPC computing landscape and you look at, data motion as a big evil actor in that, and it will be, we need to do more fine-grained data coupling, and to do that, we need to do better at in-core data exchange. So again, in-core, I mean in-memory. So you might say, well, this is easy. I can pass you a pointer. I can pass you a NumPy array. Yeah, I mean, that works between me and you, but it doesn't work across 120 people, or 120 developers and all these things. So there are some key things that can make life easier, and these were the key things that we thought would help make our lives easier. And the first one is to give us a way to describe things that we care about. Fundamentally, we care about numeric arrays. So that's what we're trying to describe. And we need a way to be able to support a mixed memory ownership semantics. And what I mean by that is I may have some data that I don't know or I can't control, but I need to be able to pass it to someone else. And I'd like to be able to annotate some of that data, maybe with some of my own. That's what we mean by mixed memory semantics. And the final thing we want to be able to do is make it a little more human-friendly by enabling higher-level conventions. So I think hierarchical context is great. It's how we interact with the web. It's how we interact with our file system. There's a lot that humans understand from that user interface, so we think that that's a good thing. Okay, so now, thanks for hanging in. Now I'll tell you what Conduit is. So again, it's focused on in-core data exchange. There's really 2 aspects to it. There's a flexible way to describe data. This data may already exist, or you may be creating it right now. And then there's a sane way to access it. So those are the 2 things that it tries to do. And it's important to note that this is sort of a multi-language data model. So I don't like the term least common denominator, but it's probably the most apt term. We're trying to do a subset of things really well, and a subset of things really well in multiple languages. And it's not a language wrapping solution, so it's not a new wrapper generator or anything like that. It's a API and a multi-language data model. So the main actor in Conduit is this thing called a node, which if you look at it, you can see what motivated this. But it can be one of four things. It can be an object, so it can have children with names. It can be a list. It can have children without names that are ordered. Or it can be a leaf, and these are explicit NumPy style arrays. You can think of it that way. Or it could be empty. It could be nothing yet. And experience with NumPy and experience with JSON really kind of created this idea about how things could be easier if we could use these things, but with some tweaks on them that we need for HPC. All right, so code, which you probably, that's not too bad. I'm going to step through just a couple examples to give you a very, very, very basic idea of what's going on here. So again, the node is the primary beast in Conduit. And in this example, we'll use it to kind of just hierarchically organize some NumPy arrays. So you can see everything's pretty dynamic. I take my X chords, Y chords, I put them in some part of a tree, and I'm packing some values from some density. This is fake data. You know, it's just not notional data for what you might have in an HPC simulation code. And at the bottom, you can see when we print it, we get this nice JSON output. All the output is JSON. And the other important thing I mentioned was this mixed memory ownership semantics. So you can either own things or not own things. So in the not owning things case, that's what we call zero copying, right? And we do that in Conduit with a function called setExternal, which sets it up to describe, sets this part of the tree up to describe that external data. So in this example, you can see I'm just showing that I changed the original NumPy array, and it's still reflected in the Conduit description of it. So it's simple concept, powerful concept. So one of the more important things that I mentioned this briefly, but it's nice to be able to annotate things, provide more context for things that already exist. And this is just a Strawman for that. So we had some data structure that we built up before from some NumPy arrays. We're adding some metadata to this now to tell you that the coordinates were actually a uniform set of coordinates, and our density was grams per cubic centimeter, and our velocity was meters per second, right? So I'm annotating these with strings. And when I do that and I come out at the end, I get this nice hierarchy, and there's ways of introspecting the whole hierarchy. So you can hand this off to somebody else without CodeGen in another project, and they can ask what fields are there and things like that. Okay, so we're aiming, and I'll say aiming, and this is a goal. It's not an end state where we're at now. We're aiming to provide an intuitive API in C++, Python, and Fortran. C is really only our path to Fortran. But this gives you an idea. I will admit that in order to write that print statement in Fortran, it took me about 30 minutes of Googling. So I am definitely not a Fortran expert, but we are using Fortran in our codes. It's important not to leave it out of the picture. And when you run those programs, you get, here's the output you get. So. Okay, so I told you our life's a little bit complicated. One of the best ways to deal with complexity is make things simpler. So that's what we're trying to do. Conduit was designed to not be a software engineering nightmare. And there's a couple choices that we made that are good for our ecosystem and maybe good for what you're doing too. One of the choices that we made is it's completely runtime focused. So there's a performance penalty for that, but again, software engineering wise, it makes life a little bit easier. We don't use CodeGen at all anywhere. So that's both a curse and a blessing, but that allows us to avoid, we have all these different codes, and if they all have their own CodeGen solution, things get complicated. And worse than that, you can have codes that might be export controlled, and you can't share those with an open source part of your ecosystem. So CodeGen in that case is hard, and you don't want to try to do it. So we made this decision to make it all runtime focused. You can think of it as metadata that is describing bigger data. That's the best way to think about it. So we have big arrays, and we have this Conduit metadata that's associated with them. And I guess what we're trying to do is not necessarily do serialization or packing or anything like that. We're trying to bring out a functionality for data description. So the fundamental thing is, how do you describe your data in core? That's it. And then on top of that, lots of other things can be built. And again, it's a multi-language data model. It's C, C++, Python, and Fortran are our current targets. But it's JSON friendly. Like all of our print statements or all of our things to and fro are JSON. If it's text, I should be clear. All right, and the philosophy again is to share your data without massive code infrastructure. So a small library, not lots of magic, and built to respect the software engineering complexities that exist in our program and that exist many other places. So, that said, there's always scope creep that happens, but luckily it's not happening in the core Conduit library. No, I'm just but many other things are very easy to do when you have this nice way of describing in core data. Those things being, serialization or I/O. So we have a couple other libraries that we're developing that use the Conduit data model in order to get us higher level services. So for example, we have this relay library that's under development, and that deals with MPI. So we can send Conduit objects, all reduced Conduit objects, all kinds of things like that. And we're also using that as our path to HDF5. Again, this works in Python or C++ or Fortran sort of the same way. So it also connects our poor C++ and Fortran world easily to the world of WebSockets, which is exciting for us. So some of our tools will be embedded web servers that have GUIs, because that's how we want to move forward. That's what everyone else is doing. We can do that in HPC as well. And then we have this library called Blueprint, which is really a repository for shared conventions. So, okay, you can describe trees of data, but that's not necessarily enough. What's a mesh look like? What is a multi-component? What are the rules for a multi-component array? Things like this. So while these won't be as much of a specification as they are runtime checks, it's important to have these, have a way of sharing conventions and have a way of validating that your data exists. This is again goes to some of the description aspects you have to do if you do everything at runtime, you have to have some way of knowing that you're not going to have runtime errors all the time. So Blueprint is a guard against that. Okay, so where are we using Conduit? So recall this slide I had earlier. So we have these multi-physics simulation applications. Again, there's about 5 of them. They're big endeavors. And they all right now basically have their own computer science infrastructure built into them. And it's a significant amount of the code that's in these. The way these applications are traditionally built is they start with the physics and then they start bolting on the computer science. And that's just been sort of the trial by fire or the crucible way of building these codes. But there is an opportunity here to take that computer science infrastructure and take what subset of it we know is shared among these codes. We have these 5 examples that provide very good use cases for us, and factor that out into a new project. And that's what we're doing with the Lawrence Livermore's ASC CS toolkit. So we're trying to look for the things that it makes sense to share. And this is an internal project now. We're hoping it will be open source once it gains more functionality. But we're actually factoring out some important key parts of these simulation codes, and we're putting them into this toolkit. And the toolkit itself is using Conduit. So it's using Conduit for describing data in core, sort of at a lower level. You can think of the toolkit as building up on some of it does much more than just what this in-core description, but the data store or CIDR aspect of the toolkit is going to use Conduit underneath the hood to do things. And in our ideal scenario, which is what we're working to prove, you'll be able to put all your data in this data store with hierarchy and context, and then you'll be able to easily share it between various physics packages and various tools. This is where we're going. And we're developing a new code called Marble, which is actually going to be the first client for this toolkit. And one of the cool things about this code is that I talked about how traditionally you started with the physics and you start bolting on the CS. And usually starting with the physics means starting with hydrodynamics. And so there's a lot of choices you make about hydrodynamics that drive all the rest of the full multi-physics process. What we're doing with this code different is we're starting with 2 different very different hydrodynamics methods at the beginning. One of them is a high-order arbitrary Lagrangian Eulerian So high order finite elements, and the other one is a high order finite difference. So these beasts are pretty different. And we're starting with that from the beginning. And this application is the first one that's going to use the data management aspects I talked about in the toolkit. All right, so another thing we're using this in is a new, I talked about a proxy app as something that's a bite-sized version of what we do in reality. Another proxy app we're developing is called Strawman, because it's meant to be burned to the ground and tried with new programming models. It's a proxy application for rendering meshes in situ. So this is, again, I have a physics code, I link in this proxy app, I can get out a beautiful volume visualization, for example. And Strawman is kind of batteries included with some of our other mini apps inside of it. So a visualization researcher can pick it up, get it going on a new computer, and then start toying with visualization algorithms. Where we're using Conduit and Strawman is for basically all the data description. So in this case, this is C++ you're seeing. But in this case, we're describing an unstructured mesh from one of those proxy apps using Conduit, and that gets handed off to our rendering pipelines to make beautiful pictures. That's the end all be all. Okay, so those are two places where we're using it. They're two important places that I'm also involved in. We're also looking at how we can use it throughout the workflow. And again, this is a tool that's just coming to life. There's been a lot of code written. There's been a lot of thought into it, but it's still a work in progress. So things we're doing now is we're proving to ourselves this actually makes sense in our applications. That's a good thing to do. And we're also catching up features in the different APIs. So Fortran's pretty far behind. Python's not that far behind. But right now, the core is all C++. So that's just the reality. Python's great. C++ is hard. We're trying to make the C++ part easier. So we also might do Lua, because Lua is becoming, quite honestly, important for our new codes. And there's a lot of other things that are on our radar. So this negotiation of these shared conventions, what's a mesh, those are very, very, very long conversations that happen with lots and lots and lots of different people. So we're taking time to evolve those, and we're taking our time to evolve those, is what I should say. Windows support isn't there yet. I'm sorry. We know the issues involved, but we're primarily HPC. We're going to try to get Windows because we need that for Visit. And that's that. So I'll go ahead and stop. So and we'll have time for a couple questions. And thank you very much. Yeah, so the question was, he's curious if the metadata is just in JSON or if the raw data is in JSON. This is a confusing question, but there really is no JSON other than when you print things. So everything is, the raw data is all basically in some tree data structure that's in core, but it's not transformed into JSON until you say, turn this into JSON. Yeah. No, actually, there can be a JSON schema that describes the data, and then it can be packed binary. So it comes in kind of in two pieces. So for MPI, that's what we do, for example. The schema goes, and then the data goes, and then you get it back out. Yeah. Thanks. So Conduit itself, probably not, because it's used at a higher level. Some of the other aspects of what we're doing, like the Strawman and all those other things you saw, those are heavily invested in performance portability across Knight's Landing or CUDA GPUs and things like that. But Conduit itself is kind of it's not trying to solve that problem. It's just trying to make it easy to describe the data. No, they haven't. So until now. Yeah.
So we have time for more questions, but if Daniel could come up and get set up, that would be really helpful.
Yeah, so the question was, have we looked into Arvo or Arrow, how do you pronounce it, or other similar? So yes, we looked at a lot of different, there's a slide I have which I won't be able to show you now, but columnar data doesn't really fit what our model is for these simulation codes. So those things require a lot of transformations to get to them. The other real key thing is Fortran, right? And there's not really good solutions in that space. So that was one of the things motivating it. All right, one more. Yeah. So the question was, in your MPI application, is there a way to help you stream larger chunks of data over MPI to other, like, so it doesn't provide a direct streaming way to do that, but what it does allow you to do is it allows you to describe your in-core data, so you can describe a subset of the data you want to go, and you can make it go there. It's not a higher level magic solution for that. But, all right, well, I'll let him cut over, and thank you very much. I'd be happy to chat with you. I'll be here for the rest of the time. Thanks.